to learn about the atom and where electrons go in an atom and what are these electrons all about and what's going on. So we're going to start out with electromagnetic radiation, EMR. You might wonder, what does this have to do with atomic structure? And when we get into about the fourth or fifth section of this chapter, it will all come together and make sense. But for now, we have to learn some background. And electromagnetic radiation is a way that energy can travel through space. This energy travels as waves, and it travels as the speed of light. There's also an idea that this energy can be a particle called a photon, which we'll learn about a little later. So what is this electromagnetic radiation stuff that we're talking about? Let's look. Most of it you are very familiar with. It's hidden behind the board. Look at that, there we go. Radio waves. That's electromagnetic radiation. Microwaves, you know your little microwave oven? It uses electromagnetic radiation. Infrared radiation, that's heat. Right in here we have all the light that we see. The colors of light are all electromagnetic radiation. UV, X-rays, gamma rays, all electromagnetic radiation. This expansion right here often confuses many people looking at this graph. Right here we've just expanded out this tiny little slit right here. That's visible light. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. Red has the lowest energy. Violet has the highest energy. So notice we have high energy on the right, low energy on the left. And the scale that we're seeing here is actually wavelength in meters. The visible light we're looking at, they're showing you a scale in nanometers, and you'll see a little conversion later, how to convert nanometers to meters. Nano means 10 to the minus 9. So all of these types of energy are electromagnetic radiation. And radio waves, we were literally talking about your FM, AM radio waves. AM radio waves are long. They're about the size of a football field. The reason you can get this distortion on your AM radio when you're driving through a parking structure is because those radio waves can't get through. They're so long, not enough waves get through, and the music gets all distorted. I just mentioned a moment ago, visible light has wavelengths from about 400 to 700 nanometers. And 1 nanometer is 10 to the minus 9th meters, or 1 meter is 10 to the 9th nanometers. We're going to get into some mathematics now. We've got some things to define. There's an equation for electromagnetic radiation. It's right here. Lambda nu equals the speed of light, where lambda, it's a symbol for lambda, is your wavelength in meters. This funny little symbol here, it's called nu. It's the frequency, has the units of 1 over seconds, or hertz, Hz. When you see Hz, you're thinking hertz or 1 per second. C is the speed of light, 3.00 times 10 to the 8th meters per second. So what is this lambda and nu stuff? Lambda is the length of a wave. So I've got some pictures up here. On the top we have a low frequency wave. So here's the wave. Here's a wave. And lambda, right here, is the distance from the middle of one wave to the middle of the next wave. You can also call it the distance from the top of a wave to the top of the next wave. It's the same exact length, and you measure lambda from a top to a top, from a middle to a middle, or you could even measure it from the bottom to the bottom. You'll see on this lower graph we have a much smaller lambda right here. This one we're showing you from the bottom to the bottom, and you'll see the lambda on the lower graph here. This lambda is much smaller than the lambda in the top graph. Now, frequency is how many waves pass through a specific point per unit of time. So these waves are not still, they're moving. So if I were to draw a line right here and say how many waves would get past this point in 1 second, well, all of the waves are traveling, for these waves, they're all traveling at 3 times 10 to the 8th meters per second. Let's look back at our equation up here, right here. So the speed of light is equal to the wavelength times how many waves pass a certain point per unit of time. Well, if the speed of light is constant, as wavelength goes up, frequency goes down. These are inversely proportional. So let's look at our graphs now. You can see the top graph has a very long wavelength. The bottom graph has a smaller wavelength. Smaller wavelength is higher frequency. Longer wavelength is smaller frequency, because these waves are all traveling at the speed of light for electromagnetic radiation. Let's do a problem, now that hopefully you have an idea of what wavelength and frequency are. So if the speed of light is 3 times 10 to the 8th meters per second, we just told you it was, calculate the wavelength of the electromagnetic radiation whose frequency is 7.5 times 10 to the 12th hertz. You might be able to do this on your own. If you can, just go ahead, pause while I solve this out. Okay, we need to assign our variables. Lambda is the wavelength. That's what we're trying to find, so that's the unknown. Our frequency is nu, and we know the speed of light. So I'm going to isolate lambda, because that's what I'm looking for, and plug in my values. 3.0 times 10 to the 8th meters per second. Frequency is 7.500 times 10 to the 12th hertz. Now remember, hertz is 1 per second, and that equals 4.0 times 10 to the minus 5 meters. I kept 2 sig figs because of this. And notice I have per second in the numerator and per second in the denominator, so those cancel, and I get my final answer. Let's do another problem. Find the frequency of the electromagnetic radiation whose wavelength is 6.9 times 10 to the minus 7 meters. This happens to be red light. So I've got lambda nu is c, and again, pause if you think you know how to solve this, and go ahead and solve it on your own while I go ahead and solve it. Okay, this time we are given the wavelength, that's lambda, and we're asked to find the frequency. So I'm going to isolate the frequency, c over lambda, and I just plug in my values. It's very easy, very straightforward. So speed of light is constant, 3.0 times 10 to the 8th meters per second. Lambda, 6.90 times 10 to the minus 7 meters. And I get a frequency of, okay, 4.3 times 10 to the 14th hertz. Where did those come from? Let's see. The meters cancel, and I have the units of 1 over second. And remember, a 1 over second is equal to a hertz. All right, we're going to move on. Section 7.2, photons. So now we're getting into Einstein. And Einstein says, you know what, we've got this electromagnetic radiation, but even though it's a wave, it kind of looks like a particle. And these particles are called photons. Photons. And we have a new equation. The energy of these photons is equal to h nu. That nu is that same frequency we just learned about a moment ago. H is called Planck's constant. You don't have to memorize this ever. It's given to you. It's always that number. And here we go. This is Einstein's idea. Light is a wave. It's a wave. See this wave here? And it's also a bunch of particles that come streaming at you, little photons that come streaming at you. Now, we have some problems. Find the energy of a photon with a wavelength of 450 nanometers. So we have to use E equals h nu, but we also know lambda nu is c. We're going to isolate nu from this equation. We get nu is c over lambda. And then we're going to plug that value into here to get a new equation, E equals hc over lambda. Now lambda, where's lambda? Wavelength is 450 nanometers. We need to convert that wavelength right over here. Remember, 1 nanometer is 10 to the minus 9 meters. So 450 nanometers is 4.5 times 10 to the minus 7 meters. I have lambda. I know h, it's Planck's constant, above. And I know the speed of light, c. If you want to plug this in, go ahead. Otherwise, I've got it solved out for you, so pause. See if you can do it. And here's my answer. There we go. And here is our last problem. Find the wavelength of a photon whose energy is 2.5 times 10 to the negative 19 joules. This is just the reverse of the other problem. All right, so last problem. We're trying to find a wavelength, and we're given an energy. So we need to use the energy equation. And if you think you know how to solve this, go ahead, pause, and do the problem yourself, and then look back when you're ready to go. So E is h nu, and we're asked for wavelength. We also have lambda, nu is c. We isolate nu, c over lambda. Substitute that in for E, for nu, sorry. E is hc over lambda. And let's plug in our values. Here's h. C is the speed of light. It's actually 3.00 times 10 to the 8th meters per second. We know that there's 3 sig figs in there. And lambda. Oh my goodness, I'm doing this backwards. I'm trying to solve for lambda. Let's start over. Why did I do that? That was not good. All right, E is hc over lambda. We're trying to solve for wavelength right here. So lambda is hc over E. Now we will plug everything in. 6.626 times 10 to the 34th joules seconds is h. C is 3.00 times 10 to the 8th meters per second. And energy. That's how I figured I did something wrong, because I was given my energy and I hadn't isolated lambda. I like to isolate what's missing. Energy is 2.500 times 10 to the negative 19 joules. And I get, by the way, I noticed as I was doing my calculation, there's a negative in front of the 34 on Planck's constant. Don't forget that minus sign. Okay, so the final answer is 7.95 times 10 to the minus 7 meters. If you put this in your calculator and you got a slightly different power right here, it was probably because of that negative 34. It's not positive, it's negative. Now, let's check our units real quick and find out, well, how did I end up with my meters? Because you should always check your units. The joules cancel. I have seconds and per seconds, and I'm left with just meters. And there we go. There's my answer. Nice short video for today.